We're now going to start the block of the course which is on ecology. And these are the titles of the upcoming lectures. You can think of ecology as providing the theater in which the evolutionary play occurs. That's a metaphor from Evelyn Hutchinson. And basically, I'm doing a top-down and then going from the top down and then going from the bottom back up to the top in going through these lectures. So I'm going to start today by talking about climate and the planet and how life is distributed on the planet, and then move from that into the biology, so looking at physiological ecology and interactions with the physical environment, leading from that through population growth, competition, predation, parasitism, up to communities. So that's sort of a way of doing a Cartesian bottom-up construction of communities, and then dealing with some of the larger scale issues in ecology, which have to do with islands and metapopulations, and then systems ecology, energy and matter flow. And then I'm going to end with a lecture which is both about the role of biodiversity in ecology, but also about general takes on the value of biodiversity. And this last lecture in ecology is going to include some stuff like an economic take on biodiversity, an evolutionary take on biodiversity, as well as the issue of does biodiversity actually help ecosystems to function better. So that's what's coming up. And today we're going to basically look at the climates of the planet, how the planet can be looked at as a set of climate machines, and how they generate the biomes on the planet. So at this scale, this stuff I think is probably pretty familiar. The world climate is, of course, cold at the poles and warm at the tropics, but there's a lot of detail in that. It tends to be warmer and wetter on the western sides of the northern continents and cooler and drier on the eastern sides of the northern continents. The influence of the Gulf Stream can be seen pretty clearly here in Europe, with this large warm area being sort of pushed up and to the right by the warm water which is coming up out of the Gulf of Mexico. And if you go far east into the huge block of the Eurasian landmass, you can get so far away from the effects of the ocean that the coldest temperature, at least in the northern hemisphere, was recorded right about here. It was, I think, minus 127 Fahrenheit, which, you know, that's nippy. There are interesting similarities in the climates of similar places. So if you look at the western leading edge of North and South America, and you go about as far south of the equator as north, basically what you run into is a temperate rainforest. There's a temperate rainforest that is stretching from Northern California up to Alaska, and there's another temperate rainforest which stretches along the coast of Chile. And these similarities in climate have created similar biomes and similar selection pressures and have led to convergences in the communities that you see in these places. So if you really want to understand why is it that if I am standing, say, in Chile or in part of New Zealand or in British Columbia, that they kind of remind me of each other, even though the plants may not be at all related. They look the same, it feels the same, the forests have similar structure. Well, you have to go back to why the planet as a whole constructs similar climates in those places. Part of it at a local level, if you're looking, say, at what's generating the rainforest in Chile or what's generating the rainforest in British Columbia, has to do with the way that mountains are interacting with atmosphere. So in these situations, you have got clouds that are coming in off of the ocean, and they are being forced upward by a mountain range. And there's some very simple physical chemistry that goes on when you force a cloud upward. The rising air is going to be cooling before it condenses. Then it will condense and form heavy clouds, and they will rain out. And as the wind is going to push them up over the top of the mountain range, basically all of the water will leave the cloud. Well, that's what's creating that rainforest. Okay? And the reason for that is that cold air can't hold as much water as warm air. And the cooling is going on at a rate of about 6 degrees centigrade per kilometer of elevation going up. The air, which was at 20 coming in off of the ocean, this is 20 degrees centigrade, is hitting perhaps 4 degrees at the top of the mountain. So you could think of this as the Sierras or the top of, say, the Cascades in Oregon or Washington. And then it falls down the other side. And over here you have dry air falling. This is wet air rising, and it rains out, and then you have dry air falling. And this wet air rising and raining and dry air falling and warming and ending up 4 degrees warmer at the same elevation on this side than it was on this side because of the heat of condensation that's been released by the rain here. This is something I want you to remember because it actually also applies at the scale of the whole planet. When you have very large air cells that are rotating on the planet, and where there is dry air falling, you're going to get deserts, and where there is warm air rising, you're going to get rainforests, whether you have the mountain range there or not. So we'll see that in a minute, and that's why I wanted to introduce this level of analysis at this point. Okay, so this warm air falling here is called Föhn in Switzerland, and the Swiss always complain that it gives them headaches. It's called the Santa Ana wind in Los Angeles, and there's a special wind that blows down the valley behind Lahaina, Maui that can hit 140 miles an hour sometimes, which is similar. So these local dry, hot winds can be very important, and they're actually what drive the wildfires in Malibu and things like that. Okay, now let's take a look at the whole planet. If the Earth was simply a stationary ball sitting in space, undisturbed, but was being heated at the equator, it would develop basically 2 convection cells, one in each hemisphere. So there would be cold air that was falling on the poles, it would be flowing down to the surface, and it would be picking up moisture and rising, and basically you would get a belt of rainforest around the equator, and you would have deserts at the poles and a gradient in between. That would be what would happen if the Earth were not rotating. The Earth is rotating, and because it's rotating, on an idealized planet, you would get 3 Hadley cells going out from the equator, 3 in the north and 3 in the south. And at the equator, you would have warm air rising, and it would be dropping rain because as it rose, it cooled, and it would lose capacity to hold water, and it would rain out. Then it would flow northward and fall at about 30 degrees north. Okay? There, it would be interacting with another similar cell that would be carrying warm air north and rising at about 60 north. Okay, remember where the rainforests were in Chile and in British Columbia. They are in this region here and in this region here. And this is where the deserts are around the world. They're at about 30 north and 30 south. Now, this is an idealized format. At the boundary, by the way, of where you've got the polar highs and the northern Hadley cell here, right at this boundary is where you get a polar front, and this is where the jet stream goes around the world in the north, and it goes around the world in the south. So the location of the jet stream that drives most of the weather that we encounter here, and the idea that it might, say, pull in a mass of a clipper of Canadian weather coming in from the polar front here, is actually generated by this structure, and it's wobbly. Okay? In an idealized world, this is all smooth and these lines are clean and whatnot, but in fact, the surface of the planet has got stuff like on it like continents and oceans, and as this stuff moves in its circulation pattern, both north and south and east, west to east around the northern hemisphere, it wobbles because it's been deflected by local perturbations like mountain ranges and oceans. So out of this, you get the patterns of wind that in fact have, they not only currently generate weather, you can really only understand the, say, the history of the last 8 or 10,000 years of human civilization on the planet by realizing that the people who were trading and were using boats to move were relying on the fact that at about 35, 40 degrees north, you can count on a west wind. At about 20 degrees north, you can count on a trade wind, and that repeats in the southern hemisphere. And this is actually, these trades here over in the Indian Ocean were what drove the trade between India and the Roman Empire, things like that. So you should think of the planet as being covered with, these are really very thin sheets. When you think, for example, that we're looking here probably at 3,000 or 4,000 miles, 4,000 or 5,000 kilometers, and the depth of this cell is actually only about 5 to 10 kilometers. So it's a very thin cell which is rotating like that. Now, if there weren't any continents, you'd end up with something that looked like Jupiter. Okay, Jupiter has these nice, neat bands that go around. And, I mean, it is a bit, it's not the perfect, smooth Hadley cell picture that I was showing you, but still, that's quite a tight band there. And these are rotating cells. Jupiter's bigger. It's got a few more of them than the Earth does. The Earth, by the way, sitting on this picture is, it's about that big. So this is a lot bigger. Because the Earth has the continents and the oceans, you don't get that smooth picture in a shot from space looking at the clouds. You see a lot of swirls and vortexes that are being caused by these local perturbations. Right here you've got the African continent coming down, you've got Antarctica down here. This is 40 to 60 south, clear ocean all the way around the planet. Winds blowing in this direction. They can go all the way around the planet with unobstructed ocean just about the whole way, except maybe just for the tip of South America. This is where you can get open ocean waves that are up to 100 feet, 30 meters high. And of course, this is also where the Whitbread round the world race goes down so that people can go really fast around the globe and take their life in their hands in pretty rough weather. So the Earth doesn't really have the idealized model of climate that I've shown you in the previous pictures. It's more chaotic, but there's still a pattern there. And I want to emphasize now some of the patterns. So of course, heat's being moved. Basically what's going on is that heat's being moved from the equator towards the poles simply by physical chemical forces to try to equalize the heat gradient that's coming in from the sun. And that's done by wind and by water. Now, as a packet of air or water moves towards the poles, it's coming with higher radial velocity. Just think about the difference in the diameter of the spinning Earth at the equator and at the poles. At the equator, the diameter of the planet is roughly 8,000 miles, so the radius is about 4,000 miles. And as you move a packet of air or water up towards the pole, by the time it gets to the pole, the diameter is 0. Okay? So in between, basically it's a trigonometric function that's telling you what's the diameter of the spinning object as I go north. So if I'm coming from the equator and I'm headed north, I have more angular momentum than the ground under my feet that I'm moving onto. It's moving slower to the east than I am moving. And if I'm standing at the poles and I start going south, the ground under my feet is starting to move out from under me because I don't have as much angular momentum. So what that will do is it will take a packet of air or water that moves toward the equator. It's coming down with lower radial velocity, and it will be accelerated to the west. That apparent force, and by the way, so going north, you'll be accelerated eastward. Coming south, you'll be accelerated westward in the northern hemisphere. This is an apparent force, okay? It's called the Coriolis force. And it's shaping the direction of major ocean currents, and it's also shaping things like the trade winds. And you'll see in a minute that it shapes the way that hurricanes spin. So I'd like you to take I want to make sure that you get this, and I'm going to ask in a minute if one of you can explain it. Okay, so could you just take a minute and explain it to your partner, how the Coriolis force works and what's really going on here? It's a piece of three-dimensional geometry, and basically it's driven by the fact that the Earth is spinning on its axis and things are moving north and south on the surface of this ball. Okay, 1 or 2 minutes. Yeah. Do you want to explain it to me?
I need a picture. I'm very good with the words here.
Come on. So here's a packet moving north.
Okay.
Let's take a slice through the equator here. And what you'd see inside here is a circle that has a radius of 4,000 miles. And if I do a slice up here, it has a radius of, say, 2,000 miles.
Right.
Okay? So in 24 hours, this thing is spinning very rapidly. It's about 1,000 miles an hour angular velocity down here, right? Up here, it has, let's see, this is 4 times 3, 12. Instead of 24,000 miles diameter, this is about 12,000 miles diameter. So it's only got 500 miles angular velocity up here. So this is coming with 1,000 miles angular velocity up into an area where the ground under its feet is moving 500 miles per hour slower.
Right.
So it's going to go like this. Got it?
Yeah, it's
Does the picture help?
Yeah, the picture helps.
Okay, I just learned that the picture is helpful. Okay, I'm going to do the picture again for you. Actually, maybe one of you can come up and help me do it. Anybody want to help me? Anybody feeling brave this morning? Bold? Life-threatening? Get up at the board with the professor? Okay, here's the planet. Here's the north-south axis of the planet. Here's the equator. The circumference of the Earth at the equator is about 24,000 miles, and the Earth is turning around once per day, which means that a packet of air or water which is sitting at the equator is moving east at about 1,000 miles per hour. We're going to ship it north, okay? It's going to be carrying heat toward the pole. We choose a convenient spot to take another slice of the Earth where the circumference of the Earth is 12,000 miles. This chunk of ground is moving at 500 miles per hour. So as this pack of air goes north, the ground underneath it, by the time it's gotten up here, is going 500 miles per hour towards the east slower than it is. So what it does is it overtakes the ground that's underneath it, and it bends to the east. Okay? And you can just play that back and forth in your head. You can go from the north to the south. You can do it in the southern hemisphere. It'll work in the other direction. Any questions on that? In order to see it, you actually have to break the motion of the planet down in your head and put yourself in the shoes of something which is moving north or south. And essentially what happens is that the ground, you either exceed the speed of the ground underneath you, or the ground goes out from under your feet if you're going south. So that's basically the Coriolis force. I once had to explain this in German, and I was just learning German. And instead of saying the Earth spins, which is okay in English, I said the Erde spinnt in German, which means that the world is crazy. And they loved it. It's totally wrong, but they loved it. Okay, the result of this is that if these motions, so here you've got the Coriolis force taking the Kuroshio current and bending it to the east as it goes north, and then when it comes down the west coast and as the California current, it gets bent to the west. And in each of the hemispheres, you establish a rotation in the ocean that looks like this. Here in the south, you have water which is flowing north. It's getting bent to the west. You've got water flowing to the south. It's getting bent to the east. So you get counterclockwise in the southern hemisphere and clockwise in the northern hemisphere. Now, on top of this, just as I showed you for the Hadley cells in the atmosphere, there's an important three-dimensional cell structure in the ocean. So north of the Antarctic continent, there is a place where the cold surface water of the Antarctic sinks at the Antarctic convergence. It's down about here. And it then forms a cell which creeps along the floors of the major oceans and then comes back up. There's a very important spot where water from the Arctic Ocean coming down from Greenland is sinking near the Gulf Stream here. And it's one of the real current issues in global warming as to whether or not this point up here, or this actually, it's not a point, but this whole sheet of sinking water is going to remain stable. Because if it doesn't remain stable and this moves south, then the Gulf Stream will get blocked, and basically England, France, and Spain are going to end up with a climate which is like that of northern Canada very quickly. I mean, that is something that could happen in a couple of years if this thing tips. So understanding that kind of movement actually has big implications for society and for the people who live in these places, who are in the hundreds of millions. Now, I want to show you two things about the general pattern. This is just repeating the overall pattern on the planet. We get hurricanes roughly where there are trade winds, and we get them both in the northern and in the southern hemisphere. And then right at the equator, we get El Nino in the Pacific. And I want to show you a little bit about hurricanes and a little bit about El Nino, because those are two of the sort of large-scale weather patterns that occur on the planet. So this question here, why did cyclones turn counterclockwise in the northern hemisphere and clockwise in the southern, is a bit puzzling, because I have just shown you that if you take a packet of air or water and you ship it north, it's going to result in a clockwise circulation in the north and a counterclockwise circulation in the south. And yet here is a nice photo from space of Hurricane Katrina starting to go over Florida before it hits New Orleans. Cyclone Larry, equally destructive, plowing into northern Australia. And you can see quite clearly that Hurricane Katrina is counterclockwise and Cyclone Larry is clockwise. And that looks puzzling, but here's the answer. If you take a standard packet of air moving south in the northern hemisphere, hitting something like Hurricane Katrina, it will come down and it will take this low and it will spin it. And if you have this as a set of clockwise forces operating on a low, they will spin it counterclockwise. And the same thing operating in the southern hemisphere will spin a cyclone in the southern hemisphere into a clockwise shape. So really, it's an interesting problem of figure and ground, or just what perspective are you standing in when you're trying to figure out why the thing is spinning that way. Because basically, it is being operated on by external Coriolis forces that are generating the antagonistic movement, the unexpected movement in the structure. But it results in, very important consequences for anybody that's in the path of one of these things. So that's basically the explanation of why we see a counterintuitive kind of spin on these big storms. Now about El Nino. I think El Nino actually is an extremely interesting and neat phenomenon. It has huge implications, and it drives weather patterns, in fact, over much of the planet. It's not just at the equator. Under normal conditions, basically what's going on is that you have the Kuroshio current in the northern Pacific, which is coming down off of California and Mexico and then going west along the equator. You've got the Humboldt Current in the southern Pacific, which is coming north along the coast of Chile and Peru and then curving out to the west, driven in those big clockwise northern hemisphere gyres and counterclockwise southern hemisphere gyres. And what they're doing, because they have a continent more or less to the right here, they are picking up the water and shoving it offshore, and that's causing the lower bottom water to well up, and they are shoving the warm surface water out to the west. And that causes a big buildup of warm water, which is out about at Guam in the Marianas, so, or all the way to the Philippines. And this pile of warm water is actually about a meter higher than the water in the eastern Pacific. It's being held there by the currents and the winds. So it's actually over a distance of about 7,000 or 8,000 miles. It's picking the surface of the ocean up, and it's stacking it up a meter higher out to the west in the Pacific. Now, under El Nino conditions, what happens is that the currents break down. And when the currents break down, the force that was holding the water higher in the western Pacific goes away, and what does the water do? It falls downhill. It flows back to the eastern Pacific, covering the eastern Pacific up with a layer of hot water. This has all kinds of consequences. One of the consequences is that warm water evaporates more than cold water, and so rainfall increases in the eastern Pacific, and cells that carry a lot of water will then get blown into places like Mexico and Arizona, and during El Nino conditions, you'll get much heavier rainfall in the American West and all the way through to the Mississippi Valley than you will during normal conditions. But another very important thing happens. This covers up the upwelling. It covers up the cold water that was coming up from the bottom of the ocean, and that cold water that was coming up from the bottom of the ocean is carrying with it all kinds of fertilizer. Basically, the bottom of the ocean has been receiving the dead bodies of algae and zooplankton and everything else for a long time. There's been a lot of nitrogen and phosphate building up down there. And under normal conditions, that's being carried up by the upwelling. And when El Nino rolls in, it covers it up, turns off the fertilization process, the algal production goes down, zooplankton production goes down, the fish don't have so much to eat, and the fishery stocks collapse. So once every 10 or 11 years, when this happens, the great fisheries of the eastern Pacific collapse. And that means that thousands of fishermen go out of work. It means that seabirds starve. And you should think of the whole Pacific Ocean as kind of ringing like a bell on about a 10 or 11-year interval. And since the Pacific Ocean occupies roughly half the planet, that means there are signatures of this that reverberate all the way around the planet on about a 10-year interval. When I was doing my PhD on the evolution of mosquito fish in Hawaii, I had 60 years of records of the level of sugar plantation reservoirs in Hawaii. And I did a time series analysis on it, and I picked up two very dominant signals. There was a short frequency signal, which was the weekends. That's when people went home on the weekend, so the reservoirs didn't fluctuate on the weekends. But there was an 11-year signal that was El Nino, and it was the biggest, strongest signal in the data. So up in Hawaii, which is really quite a ways away, on this map, Hawaii would be up off the map up here somewhere. This is making a big impact on the 10-year rainfall record. And it's doing so in Arizona and New Mexico and Texas and California as well. Okay, so that's El Nino. And to see what it looks like, this is a NOAA picture of the temperature of the Pacific going from the eastern Pacific out to the western Pacific. And these are different years. So this is starting in 1986 and going up to 2001. And this year right here, where you see a big tongue of warm water, 29 degrees centigrade, pushing all the way back in to the eastern Pacific, is 1997, one of the major El Nino events. And in fact, there is right now, I think in the last year or so, another El Nino event. Yeah, Myra? There appears to have been this kind of cyclicity in the Pacific for as long back as we can see in the records. I think that the things that would probably make it break down are plate tectonic events. I do not know if El Nino was regular before the Isthmus of Panama formed about 10 million years ago. I suspect it would have been different. And this is just that, this is the actual temperature, and then this is the deviation from the normal. And by the way, they call a year that's sort of really supernormal La Nina. So this is a La Nina, and this is El Nino down here. So you should think of La Nina as being cold water in the eastern Pacific, and El Nino as being hot water in the eastern Pacific, with all of its consequences. Now this process that I just described, where the upwelling is interrupted, happens in El Nino. In La Nina, you've got the upwelling going, and in El Nino it's interrupted, and of course that would be happening basically right along here. But upwelling is normal in much of the planet, and it happens along coastal margins. So the areas here that are indicated in red is where cold, deep water is being moved to the surface by various forces, and in the process is fertilizing the surface layer. And that's driving the productivity of the world's oceans. So people, of course, have discovered this. I mean, one could have made a theoretical argument, but in fact, the world's fishermen discovered this long before there was any climatic theory. And the greatest productivity in the world's oceans are in places like the North Sea, the Benguela Current, and the west coast of Africa, the coast of Peru with its gigantic anchovy fishery, west coast of North America with tuna and sardines and things like that. And you can see a few other spots around the world that are very productive. Fishing is mighty good in New Zealand. The way this works is through a combination of offshore winds and the Coriolis force. So let's first do the offshore wind. If you have any body of land and you have wind blowing offshore, it pushes the surface water off, and just in order for gravity to equilibrate the water pressure, it's going to therefore pull up deep water at the shoreline. And if any of you live on the West Coast, I think you know this perfectly well, because you know that very often the water on the shoreline of the West Coast is colder than the air, and it is going to produce fog, and all the way from roughly Santa Barbara up to Juneau, you have fog banks, which is because you have cold water hitting warm air. And it's that cold, upwelling water hitting the warm air that makes the fog, which is so characteristic of the west coast of the United States, and is also characteristic, by the way, of the west coast of Namibia. There are even some beetles that live in the desert of Namibia that are specialized for catching the fog on their feet. They stand on their heads and they put their feet up and they catch water with their feet, because it doesn't rain in Namibia. Now, if we were to look at, say, the coast of Oregon, and we have wind or current, which is coming south, we're in the northern hemisphere, we're going south, the Coriolis force is working, and because we're coming south, we have less angular momentum than the Earth under our feet, and therefore it's going to be diverted out to the west. That means that there's going to be a tendency for the Coriolis force to suck water offshore, and the wind or the current could be coming south, but the net vector of movement of surface water will be deflected off to the right by the Coriolis force and pulled offshore. And so you're going to get cold bottom water welling up to the surface and fertilizing things. Okay, that's a little bit about how the climate machine is working in the ocean. Now let's take a minute to look at what it's doing to the biomes on the surface of the planet, on the terrestrial part of the planet. Ecologists have broken the planet down into areas that basically look similar from the structure of their ecological communities and are thought to be similar in terms of the general control of ecological processes. So you've got ice sheets, of course, then you've got tundra. In tundra, you normally don't see plants that are taller than 10 or 20 centimeters. You have things like dwarf birch, lots of moss, things like that. Often tundra is overlying permafrost. Then you've got the taiga, or the northern hardwood forests, which stretch across much of the high latitudes in the northern hemisphere. You can't really get to these places in the southern hemisphere, okay? Antarctica is too cold, and Africa and Australia don't really go far enough south. There's a little bit of replication of this in South America, but it's mostly a question there of altitude. Then you get some forests that are extremely similar in eastern North America, across Western Europe and into Central Asia, and in China and Manchuria, which is temperate broadleaf forest. You get similarities in the rainforests of the Amazon and the Congo, and in Southeast Asia, and in northern Australia, and so forth. There are, in other words, these large biomes around the planet that are mainly shaped by climate. And I'm just going to touch quickly on two of them. One of them is the desert biome, and one tends to find deserts at about 30 north and about 30 south. So of course the Sahara and the Arabian Desert are at 30 north. The deserts of Mexico and Arizona are at about 30 north. The Chilean and Peruvian deserts, the Atacama Desert, are at about 30 south. The Kalahari and the Namib are at about 30 south. And the Great Central Desert of Australia is at about 30 south. And remember, this is where you have cold air falling. At the equator, you have warm air rising, and where you have the deserts, you have cold air falling, and there's very little water in that cold, dry air that's falling. It's quite hot during the day, and it's cold at night. So, for example, if you're in the hot desert of Central Australia, and it's nightfall, on a nice clear night, the temperature will go, say in Fahrenheit, from 80 or 90 degrees down to freezing in about 2 or 3 hours. And so Aborigines learned to do things like all sleep together in a big bunch. The wet tropical forests are about at the equator, where you have warm air rising, warm moisture-laden air is rising. There are some interesting twists on that. For example, if you take a packet of air off the South Atlantic and you blow it into the Amazon actually will transpire the moisture in that air. The trees in the Amazon will transpire it, so that by the time a packet of rain that started here in the South Atlantic hits the Andes, it's been rained out 3 times. It's gone back up into the atmosphere, made a cloud, gone down into the ground, gone up into the atmosphere, rained out, made a cloud, and it's done that about on the average 3 times by the time it hits the Andes. So there's some interesting local stuff going on. But roughly speaking, you find the world's greatest biodiversity near the equator in these rainforests. And so if we just take a look at one of them, the Corcovado rainforest in Costa Rica, and all of you are eligible to go on an OTS course to Costa Rica, and as part of it, you will probably go to the Corcovado. Or, if you were lucky enough to be in Rick Prum's class this semester, you got taken by Rick over spring break to Ecuador, where they logged 450 species of birds in 10 days. And in that kind of habitat, you are going to run into extremely high species diversity, and you're going to see all kinds of stuff that you just never run into in the temperate latitudes. So I strongly recommend a visit to one of these places if you possibly can. For a biologist, it's pretty much this and, say, going over a coral reef, especially at night, it's kind of like Christmas, because every time you turn around the corner, there's another surprise under the tree. And there's something beautiful and strange that you've never seen before. So this is the biological consequence of a long period of fairly stable, warm, moist conditions, which are the ecological theater that has allowed this kind of evolutionary play to take place. If we look back in time, there are a couple of things about, say, this is roughly the last 50 million years, from the Eocene up to the Holocene. There are a couple of fairly neat things that have happened in terms of the global pattern of climate. One of them is that if you go back to the Eocene, when it was really quite warm, and you had temperate forests that went right up to the Arctic Ocean, you can demonstrate that there were large trees growing in northern Greenland at a latitude where it was dark for nearly 6 months a year. It was warm, but it was dark. And that really is a rather interesting comment on what trees are capable of, that you could make a tree that would live in complete darkness, not doing anything for 6 months, and then turn back on and become actually quite a tall forest. These trees are 2 meters in diameter in northern Greenland. So that's one kind of thing that the historical look at ecology will give you. But there's another one which is really, I think, important for everyone on the planet now, and that is that the Eocene, Oligocene, and Miocene were all pretty warm. In fact, they were much warmer than the Earth currently is. And when you look, say, at the distribution of tropical forest, which is in green, you can see that tropical forests covered really most of the Earth for tens of millions of years, and compare that to their distribution now. We're essentially in an interglacial in the Pleistocene right now. The planet is really much colder than it has been on average. And you can see those sorts of trends written in the distribution of the biomes across the planet. And it would be terribly neat to have a slow motion videotape taken from a distant satellite over the last 65 million years to see this kind of thing going on. One would have to be, of course, a bit patient. So, here are the things I want you to remember about climate, organisms, and the climate machine of the planet. If all you know is the seasonal pattern of temperatures, daylight, and water availability, you can predict a lot about what you're going to find in terms of biomass, in terms of biome, all that kind of stuff. I would like you to remember out of this lecture and out of your reading how mountains create rain and rain shadows and hot downslope winds. I'd like you to remember the pattern of winds and currents from the equator to the poles. I'd like you to remember how the so-called Coriolis force works, how El Nino works, this wonderful thing of piling up a meter-high mountain of hot water in the western Pacific and then letting it fall back down, how ocean currents drive upwelling, and why cold, nutrient-rich water will well up at the edge of a continent or an island, and how the climate structures the biomes on the planet. Okay.